Traditionally speaking, navies around the world built warships entirely from steel. But the rapid advancement of computers and other electronics had a profound impact on the warship's design, and it's not what you think. Early computers and related equipment, like radars, sonars, and weapon systems, were quite bulky and required a lot of space. The increase in the amount of electronic equipment that needed to be installed on ships had a significant impact on the size of the ships, mostly due to the volume of space required. But this new equipment, and more importantly, antennas, had to be placed correctly in order to avoid interference. You can't just place them anywhere. Moreover, the radiation emitted by powerful radars also became of concern, which further complicated superstructure and mast arrangements. All of this new topside equipment resulted in a higher vertical center of gravity, which affected the stability of the ship, and that problem had to be fixed. The solution was to build lighter aluminum megastructures on top of the steel hull, which would lower the center of gravity. Despite warnings against using aluminum, the US Navy proceeded to build numerous classes of ships with steel hulls and aluminum superstructures. But little did they know at the time that this decision was a ticking bomb that would affect the entire aluminum fleet. The first reality check with aluminum occurred in November of 1975 when USS Belknap collided with aircraft carrier USS John F. Kennedy that killed 8 sailors. The cruiser's aluminum superstructure simply perished in flames, which lasted for 2.5 hours. While aluminum doesn't burn, it has a melting point of just 640 Celsius or 1184 Fahrenheit, compared to 1450 Celsius or 2642 Fahrenheit for steel. More importantly, aluminum starts losing its mechanical strength in temperatures as low as 150 Celsius or 302 Fahrenheit. No wonder that aluminum decks and bulkheads melted and collapsed in the path of a fire. 2 years later, in 1977, the Royal Navy experienced its own reality check with aluminum aboard a new Type 21 frigate which used aluminum alloy in its superstructure to reduce weight. A fuel leak caused a major fire in the engine room of HMS Amazon. The blaze distorted the aluminum ladders, and that prevented firefighters from reaching the fire in a timely manner. As a result of the incident, the Royal Navy reverted back to using steel in ships' megastructures. In 1982, during the Falklands War, 2 more Type 21 frigates were lost during combat. The loss of both HMS Ardent and HMS Antelope was attributed to their aluminum superstructures, but that is not what actually happened. HMS Ardent was lost due to multiple waves of air attacks that disabled the ship's weaponry and propulsion systems. The damage was catastrophic, so a decision was made to abandon ship. While HMS Antelope survived the air attacks, it got hit by a 1,000-pound bomb that failed to explode. The first 3 attempts to remotely defuse the bomb failed. During the 4th attempt, a small explosive charge was placed on the fuse in order to disable it, but it ended up exploding the bomb, which in turn split the ship in half. The commanding officer gave the order to abandon ship, and only 5 minutes after the last person left, the missile magazine exploded. Another myth is that HMS Sheffield was lost due to aluminum superstructure that made her more vulnerable. The truth is that HMS Sheffield had an all-steel superstructure, but even that didn't save the ship from a massive fire that eventually sunk the ship when it was hit by an Exocet missile. In fact, out of the Royal Navy's 9 ships sunk during the Falklands War, only 3 had aluminum superstructures. If this tells us anything, is that with modern weapons, it just doesn't matter what the ship is made of, as the weapons are just too lethal. Take a note of this incident, as this will be pivotal when we later talk about why the US Navy resumed building ships using aluminum. In 1987, the US Navy made headlines as it announced that it will build its new Arleigh Burke destroyers entirely from steel. The aluminum industry was furious, calling it a short, fat ship with reduced speed and maneuverability. In response, the US Navy defended their decision by citing that all of the 263 frigates, destroyers, and amphibious ships with aluminum superstructures had experienced cracking, every single one of them. The issue was twofold. Joining an aluminum superstructure with a steel hull sounds easier said than done. Due to dissimilar melting points and expansion coefficients, welding aluminum to steel is very difficult, but it can be done through special joints or friction welding. Galvanic corrosion also comes into play when joining two dissimilar metals, but more on that later. But once you get over the first issue of welding aluminum to steel, the second issue is that steel is more resilient to stress compared to aluminum. In heavy seas, ships flex, bending downward in wave troughs and upward on crests. This puts a lot of stress on the ship, and while a steel hull can absorb the energy by flexing and returning to its original form, aluminum cannot, as it stretches and cracks. Oliver Hazard Perry-class frigates and Ticonderoga cruisers probably experienced the worst cracking of all. According to the US Navy, the average cost of alterations was about $450,000 per ship back in 1987. The aluminum industry once again fought back, saying that cracking was a design problem and not a material problem. Putting the bias aside, it appears that the industry was at least partially correct. Ticonderoga-class design was simplified by putting a huge superstructure on the Spruance-class destroyer hull, which overloaded the ship. The idea was to save money on design, which resulted in waste of money in the long term due to cracks in the superstructure. In 1985, the US Navy's Survivability Review Group officially concluded that aluminum ship structure was highly vulnerable to fire spread and loss of strength, so the decision was made to require all deck houses and superstructures to be made of steel. So engineers had to figure out a way to put all of the Ticonderoga's gadgetry, primarily the Aegis combat system, into a wider hull of a destroyer. The shrinkage of electronic equipment helped with that goal. In the early 2000s, the government reversed its policy of requiring ships' megastructures to be built from steel. This impacted the two new classes of littoral combat ships. LCS-1 Freedom Class was to have its megastructure built from aluminum but have a steel hull, while LCS-2 Independence Class was to be built entirely from aluminum. But why build these ships from aluminum given the many issues that had already been experienced? First thing to consider is that both LCS-1 and LCS-2 are expendable vessels, as they are graded at level 1+ on survivability scale. If you're not familiar, there are 3 survivability standards in the US Navy. Level 1, low survivability vessels that include replenishment ships, mine and patrol craft. Level 2, medium survivability vessels such as frigates and amphibious ships. And Level 3, high survivability vessels such as cruisers, destroyers, and aircraft carriers. Level 1+ refers to ships that need to rely on sensors and speed to avoid being hit. If hit, the ship would withdraw from battle or even conduct an orderly abandon ship procedure, unlike the ships designed for higher levels of survivability. But critics say that in today's world of missiles, it doesn't really matter how fast you can go, as missiles will eventually get you. In case you're curious how damage from missiles look like on an aluminum ship, here is HSV Swift from 4 reported shoulder-fired rockets. The second reason that littoral combat ships use aluminum is that despite its shortcomings, aluminum has some advantages, the biggest of which is its density, at 1/3 that of steel. A lighter ship means lighter overall displacement, meaning that smaller engines can be used. Smaller engines mean more room for additional equipment such as weapons and sensors. No bias here. According to Austal, the company that built the aluminum ships, aluminum hulls offered 21% fuel savings per year on a 56-meter aluminum hull patrol ship versus the equivalent steel hulls. Aluminum is also non-magnetic, which reduces susceptibility to mines. The third advantage is that aluminum is inherently a corrosion-resistant metal, as a protective aluminum oxide layer forms on metal surfaces when it's exposed, which actually protects the metal. Thus, aluminum vessels do not need to be painted above the waterline, which reduces maintenance. But what about all the downsides of aluminum, such as galvanic corrosion, low fire resistance, and cracking? Well, it's been decades since the first aluminum superstructures were installed on the US Navy ships, so many lessons have been learned. Or have they? The first 2 ships of the Independence class suffered from aggressive corrosion, especially around the water jets. The issue was caused due to galvanic corrosion caused by the aluminum hull being in contact with the stainless steel propulsion system, with seawater acting as an electrolyte. Austal, the company that built the ships, insisted that it was not poor craftsmanship that led to the corrosion, but poor maintenance. Austal's CEO said in an interview that his company built 230 vessels of this type that had not suffered from this type of problem. We actually checked and verified that statement as true, as you have to look no further than the Expeditionary Fast Transports, or EPFs, built by Austal for the US Navy, which have aluminum hulls and do not suffer from corrosion. As of March 2021, it appears that the corrosion problem on the Independence-class ships was fixed by installation of cathodic protection system and anti-corrosion surface treatments. But still, steel is undeniably superior to aluminum given its thermal properties. But the thermal issues with aluminum can be mitigated. A good example is the Space Shuttle, which was built from aluminum. The Space Shuttle experienced temperatures in excess of 1600 Celsius or 3000 Fahrenheit during its re-entry to the Earth's atmosphere, but thermal protective tiles prevented the shuttle from melting. Independence-class ships use remote fire suppression systems and ceramic fiber wool systems in key areas. Based on the Navy's testing of fire insulation on the LCS-class ships, it is unlikely that an internal fire would cause major damage to the aluminum structure. However, the US Navy has not assessed the likelihood of a major structural damage caused by a weapon-induced fire. Lastly, the cracking of aluminum can be prevented by proper design and quality craftsmanship. While there have been reports of mild stress cracks of the aluminum superstructure on the Freedom-class ships, which were consequently addressed by design changes, it was actually the steel hull below the waterline that experienced the biggest cracks, ranging from 3 to 6 inches. It is possible to design a ship using aluminum that will last for a long time without major problems. Just look at the Hamilton-class cutters that lasted over 40 years with aluminum superstructures sailing in the roughs of the Bering Sea. In fact, all of the cutters are still in service either with the United States or other countries. Some cracking was noted, but nothing that couldn't be fixed. But that said, the newest Legend-class cutter is made from steel, so there's still some considerations for steel. In 2016, the US Navy conducted full ship shock trials, and both Freedom and Independence classes performed outstandingly. With no major damage, both ships returned back to port on their own. But if you dig a little bit deeper, the shock trials did reveal critical shock deficiencies, the details of which are classified. What is publicly known is that Freedom-class shock trials stopped after 2 out of the 3 scheduled blasts. The third blast, which was designed at 66% of the maximum force the ship was designed to handle, was deemed to be too risky and was subsequently cancelled. The Russians recently unveiled an Admiral Gorshkov-class frigate which has a superstructure built from composite materials such as carbon fiber. Russians claim that carbon fiber exceeds steel in terms of physical properties, but Elon Musk's SpaceX disagrees with that evaluation as they ditched carbon fiber and used stainless steel on the starships. So, what should we make of all this? The reality is that if a small diesel submarine can sink an aircraft carrier during wargaming exercises, is it really necessary to debate survivability of steel versus aluminum? As the events during the Falklands War show, a hard hit can sink any ship, regardless of it being made of aluminum or steel. With that said, the United States Navy is adding an extra 300 tons of steel to the design of the new Constellation-class frigate in order to increase its survivability. But the question is that enough to save a ship from modern anti-ship missiles during an actual war? Hopefully, we'll never find out.